with that, I will just.
I'm sorry, but you have to add.
He's also the Omega by chair professor.
Thank you.
I know what you wanted. So, with that brief introduction, please tell us.
Well, thank you for that very kind introduction. Great to be here again. And yeah, okay, it's always a pleasure to be back here. So I'm going to talk about, as it says, topological order, and the main subject of the talk is motivated by high temperature superconductivity. But I find that the moment I start talking about the details of high TC superconductivity, people get lost because it's a very confusing subject. So I'm going to present it more of a theoretical problem and then save the high TC part towards the end. And I'm going to do it in a way that I'm going to try to explain what topological order is in very the simplest terms I know, by really viewing it as a problem in statistical mechanics. So I hope everyone will be engaged. Okay, at least for maybe the first 2/3 of my talk, I hope. All right, so in fact, I'm going to begin really in classical stat mech, parts 1 and 2, where I just talk about simple, very basic stat mech models that are covered in standard graduate stat mech books. And we'll use this as a tool to introduce the idea of topological order, which in some ways is a very old idea, but recently has found much greater application in many quantum systems, and eventually I'll talk about the application to the Hubbard model, which is a basic model of electrons relevant for high temperature superconductivity. All right, so let me talk about the classical XY model. So this is the basic textbook model. You take a cubic or a square lattice. I'll limit myself to 2 or 3 dimensions. And on each side of the lattice, you have an angle, theta. And there's a very simple interaction, nearest neighbor interaction, tells you that the angles like to be parallel to each other at low enough temperatures. So this angle could be an actual angle of the electron spin, which is the point of view I guess I'll take eventually. But it could be the phase of a boson, in which case this describes superfluidity, describes magnetism, and so on. So it's a very common, basic, classical stat mech problem. So what do we know about this model? Well, we know basically everything, but let me quickly review the basic points. So in 3 dimensions, this model exhibits a phase transition as a function of temperature. At low temperatures, all the spins line up, and we have a phase with long-range order. But more precisely, the statement is that the spin correlations, here psi is e to the I theta, go to some constant even when this Ri and Rj are well separated. So this is the basic statement of off-diagonal long-range order or Bose condensation, and it's convenient to just fix the phase to have some value so that even a single field operator is condensed. So that's the low temperature behavior, and that's what we call long-range order. And in the high temperature behavior is very different. So this decays exponentially to 0, and the condensate value is 0, and this we call short-range order. Okay? And so and we can, just by comparing these two, we know there must be a phase transition. And so this is the classic example of a phase transition associated with the broken symmetry. There's a broken symmetry, which is the common angle that all the spins take at low temperatures. All right? Okay. And we also know the phase transition at TC extremely well. In the modern language, it's a conformal field theory, but I'm not going to say anything more about it. So understanding that phase transition led to the Nobel Prize in 1982. Okay. So now let's take the same model in 1 lower dimension in d equals 2. And now and 3 and above, basically the behavior is, as I said, except the phase transition is a little different. In d equals 2, however, there's something very different. There is no broken symmetry. There's no strict long-range order, and there's no Bose condensate for any non-zero temperature. But nevertheless, there is a phase transition, which is called the costless-Thouless or the Berezinski costless-Thouless transition. And what happens at this phase transition is that the two-point correlator always decays to 0, but it can decay either exponentially or with the power law. And the point where this changes is a phase transition. It's a very subtle high-order phase transition where we go from what's often called quasi-long-range order, because this decays quite slowly, to short-range order for t greater than tkt. Okay, so I mean, this is a good enough description of a phase transition, but what Costless and Thouless showed was this phase transition is really intimately connected to topology. And the quasi-long-range ordered phase, by some people's definitions, is a phase with topological order, because it's a phase in which certain topological defects are very rare. So the basic topological defect here is a vortex, where the spins wind around by 2 pi around this vortex core. So this is a vortex, and that's an anti-vortex. And in the high temperature phase, the reason you have short-range order is because these vortices disrupt. There's so many of them that the spin correlations become exponential. So it's the proliferation or condensation of vortices that gives you the high temperature behavior. And in the low temperature behavior, the vortices are there, but once you renormalize out to sufficient scale, they're only tightly bound vortex, anti-vortex pairs, and you can ignore them at the longest scales. And so you simply have what are called spin wave fluctuations, and those in 2 dimensions are enough to destroy long-range order. That's a calculation just of a Gaussian scalar field, and it gives you power law correlations. Okay.
But the theory is very, very non-topological. I mean, there's the dynamics of the spin waves.
Yes.
So there's a lot of stuff in
Right. Okay. So this is a perfect question and right point. This is why you're calling this topological order. My first answer is it's not me, it's the Nobel Committee who declared this, who called this topological and awarded the Nobel Prize last year. But a better answer is that you're true in a truly infinite system. It's just spin waves. All you need to know about the spin waves. And in fact, you don't even need to know the spin wave is periodic. But suppose I take the system, put them on a torus, then I do need to remember that theta and theta plus 2 pi are the same, and that the partition function depends crucially on that. And so there is, the finite size spectrum has memory of the topology and the absence of vortices. So the topological order is the fact that the vortices are not there. So we're going to, and that's the point of view I'm going to take the rest of my talk, that topological order is suppression of defects of some type while not breaking symmetry, of course. Anyway, this is a very useful point of view. I mean, you may not like it. It's a question of taste for this particular problem. But it's a point of view that generalizes, I think, very well. So jumping ahead a bit, some people say topological order is degeneracy on torus of ground states. Well, that's true, but that's a definition that only works for gapped system. If you have a gapless system, there's often cases where you definitely need the idea of topological order. And this is a gapless system where the pure spin wave case and the topological case will have different finite size spectra because of the periodicity conditions. Anyway, okay, it's semantic. We're free to call what I'm using a definition of topological order that maybe is not entirely appropriate, but I'll just appeal to higher authority. But more seriously, as I said, my ultimate aim is to talk about systems that are gapless, like metals with Fermi surfaces. And then there are a bunch of effects which are present in topological system with a gap, which also survive when there's no gap. And it's completely sensible to think of them as topological, and that where this definition actually works is better. All right, so that was just a review for everybody, I presume. So now I want to ask the following questions. Here's an XY model in 3D. Let's go to 3D. And now the question we want to ask in classical system in 3D, can I have topological order? Is there any way to have topological order? And I'll take the point of view that that suppression of defects may be one way to characterize it. All right, so now what happened in 2D was that spin waves were enough to convert long-range order to quasi-long-range order. That's not true in 3D. There is a long-range ordered phase. So at least to begin with, you only expect long-range order and short-range order. And so the question is, can there be another short-range ordered phase which has exponentially decaying correlations with no condensate? So in terms of the properties I've written down here, they're identical. But nevertheless, because of some topological character, I'm guaranteed to have a phase transition. All right? Can there be some other criterion? And it's not so easy to come up with criterion, but okay. So this is what I want to give an example of an XY model where there is a phase transition where nothing to do with, where all these things are true, but nevertheless, just by looking at certain properties, you can be sure that there's a phase transition.
Didn't have the XY model, but had something like the O3 model.
Yes.
And we could have other kinds of defects.
Yes.
And so on. Then one can sort of try to see how this might.
Right. So things become a little more complex. XY I picked because it's simple. If you took O3 or other symmetries, it's not obvious how this would generalize. But it does but let me talk about this case. So yeah. So it's not an accident that I'm talking about the XY model because it's the simplest case. All right. So it turns out, and I'm going to show you how this works. There is a way to guarantee that there's a phase transition and have a phase with topological order. And just like in the costless-Thouless transition, the topological order is associated with suppression of certain defects. So in the low temperature phase of the XY model in 2D, there were no vortices. Now here, if I have no vortices, if I say, okay, no vortices, only spin waves, then you can show that you will have a broken symmetry. Because if there's no vortices and only spin waves, then you can see that the spin wave fluctuations are infrared finite and they don't destroy the long-range order. So you'll be back in this phase. Unlike in 2D, where you could just get rid of the phase just by spin waves, here you can't do it. So you have to have vortices to destroy the order. But maybe if you can get away, it turns out what you can get away with is only having some of the vortices. So here I only allow even vortices that are widened by 4 pi rather than 2 pi. And here I allow all of them. Okay. So this is the claim. Now let me show this. How do we guarantee there's a phase transition, and what is the order? How to distinguish the phases? Yes. Yes. Please. No, he asked a different question, but that's certainly an excellent. Well, topology, because the vortices are topological defects, meaning that you have some, so you have some region of space where the spins are varying smoothly, okay, at far away. So then you take a big contour far away, and you take this on this contour. So here actually I should say I'm talking in 3D of vortex lines, not point vortices. These are lines, okay. So I have some angle at every point in space. And so I'm taking grad theta dot dr. Now since theta is periodic, this is guaranteed to be 2 pi times n. Okay, so this number n you can say is a topological invariant because it doesn't matter how much you distort it smoothly. It doesn't matter where you take the contour. For any given configuration of spins, this will be some number. So this number n is the number of vortices that are inside. So that's why we call the vortices topological defects, because they're associated with the topological invariant, some integer, which is independent of lots of smooth deformations, of changes of metric, and all of that. Okay.
Sorry, just to ask.
Yeah.
In 3 dimensions, of course, instead of vortices, you will have the vortex.
Oh, these are vortex lines. These are vortex lines.
They will cost, unless they will cost an infinite amount of.
So let's imagine they're closed loops. Yeah. So there's lots of loops. I should say vortex loops. Right. But pretty soon we'll think of this as a quantum system, and then they're point particles. And that direction will become time.
So in the KT transition, there's this classic energy entropy calculation.
Just to conclude, so in 2D, when you think of the quantum transition, the vortex is actually an instanton. It's a tunneling event. Now it's a particle. Yeah, sorry, go on.
So there was this energy entropy calculation which
Yes, yeah,
Subir.
yes, yes,
So this must be much more sophisticated.
Yes.
It's about even odd vortices, so there cannot be.
yeah, well, right, okay, you'll see. Yes,
That means the vortex and anti-vortex system already
is what?
vortex as well as anti-vortex system.
Yeah, if you take a section of it, yeah, that's right. But the vortex loops can become very big, and
So the proliferation would mean there will be too many things.
yes, you have lots and lots of vortex loops of all sizes, and